All right, 4.3. Yesterday we talked about linear functions or linear patterns, so today we're going to talk about nonlinear patterns. Okay. All right, so obviously nonlinear means that it is not in a straight line. We have lots of different options for it to be in. Yes?
Are we writing a line today?
Nope, not yet.
Okay.
The only graphing you have to do is plotting some points, and that's it. Okay, so now, continuing on. So, not in a straight line. A graph that you might get that is not in a straight line is what we call a parabola. It makes a U on your graph. This graph is a y equals x squared graph. It's technically called a quadratic. We're going to spend months doing these this year. You're going to love it. Okay? The second type of nonlinear graph you might see is what I call an S-curve, gentlemen. It's what I call an S-curve only because it reminds me of being out on the roads and the S-curve on the roads. The graph looks like this. It curves to the side. This is y equals x to the third power. Another possibility is a graph that comes down and makes a W. This is y equals x to the fourth power.
Is there a fifth?
Oh yeah, but we're not doing fifth today. The other possibility that could happen is that we could have what we call an exponential function that grows really quickly, or an exponential function that decays really quickly and curves. Those are our two possibilities. Now, the way we write these are y equals whatever the multiples are, so I'm going to say like a multiple of 2, raised to the x power. That's why we call it exponential, is because the x is in the exponent.
What's x power?
Your exponent is an x. Yes. Okay? Yes. Oh, upside down? It would be a negative. A negative makes it go upside down. Yep. No. If it was in negative x in parentheses squared, it would be the same thing. But no parentheses, it is not, right? Okay, so moving on. What I wanted to talk about is I'm going to go up to these top three first. This is where I want to start. Yesterday I told you that I wanted you to do the process column or the loops. You had to do one set of loops and they all matched. That meant it was linear, which was x to the first power, right? This one, it's x to the second power. It's going to take 2 sets of loops before they all matched. So then when it's x to the third power, it's going to take 3 sets of loops. Yep, 3 sets of loops. The next one is 4. 4 sets of loops before they match. All right. So let's talk about the exponential one. Gentlemen, exponential. The loops never match. And it is increasing or decreasing by multiples. So this is a special one that you're going to see today, which we're going to talk about. But I want to start with the first 3 first. First 3. Just put a curve and you're fine. All right. So here's how I want to explain it. So here's my table. I have x and y. say I have 0, 1, let's say 1, 2, 2, 5, 3, 10, 4, 17, and 5, 26. And we want to write a function rule for this. So we need to find out if it's linear or what it is. So we're going to do our loops. So we're going to start here. 2 minus 1 is 1. 5 minus 2 is 3. 17 minus 10 is 7, and 26 minus 7 is 9. Do they all match? No. So it's 1, it's not linear, and 2, we have to do it again. So now we're going to take those numbers. 3 minus 1 is 2. 5 minus 3 is 2. 7 minus 5 is 2. And 9 minus 7 is 2. Yes, it is y equals x squared. Now, remember when we did linear, the number that matched was your coefficient. That only works for linear, okay? When we talk about a quadratic, the number of loops is going to tell us what our exponent is. Then, of course, we have to decide how much we have to add on. So what do we add on, or where did this start at? 1. So we have to add on 1, right? So let's check and make sure it works. So if I take 4 and plug 4 in for x, I get 4 squared, which is 16 plus 1. Does that work? All right. If I take 5, plug that in. 5 squared is 25 plus 1 is 26. It works. Okay? Try one more like this. Do this table. I have x and I have y. I have 0, negative 2. I have 1, negative 1. I have 2, 6. Hold on. 25, 4, 62, 5, 123. I want to make sure it works. All right. So now we're going to check this one out. Obviously, you guys all told me already. You can see it's not linear. But we need to figure out what it is. So we're going to start at the beginning, and the first couple are tricky, so be careful. Negative 1 minus a negative 2. I wrote it down. Check it out. It is 1, right? Because we have a sandwich happening here. It's negative 1 plus 2, or 1. 6 minus a negative 1 is 7. Good. 25 minus 6. Awesome. 62 minus 25. And 123 minus 62. Okay. Do they match? Oh, we got to do it again. All right. 7 minus 1. 19 minus 7. 37 minus 12, or 37 minus 19. Good. 61 minus 37. 24, I agree. Do they match? Okay, let's do it again. So 12 minus 6 is 6. 18 minus 12 is 6. 24 minus 18 is 6. How many sets of loops did it take to get a matching number? So what is our exponent? X to the third power. So this is y equals x to the third. Very good. Nice job, you guys. So, yes, one of the things you learned yesterday, that starting spot works on everything we're talking about, right? All right, now I want to talk about an exponential one because that doesn't fit our pattern. It doesn't fit anywhere in our pattern. So, not yet. Relax. Okay, here's my next table I want to talk about. I'm not doing any examples yet. I'm giving you ideas of what they could look like. All right? So let's say I have 0, 1, 3, 2, 9, 3, 27, 4, 81. We'll do that. Okay, so first of all, we should try our loops and see if they ever match. So 3 minus 1 is 2. 9 minus 3 is 6. 27 minus 9 is 18. And 81 minus 27? Good. We drew it again. 6 minus 2 is 4. 18 minus 6 is 12. 54 minus 18 is 36, right? Do it again. 12 minus 4 is 8. 36 minus 12 is 24. And so we get all the way to the end and they never matched. So that means it's got to be exponential. So we got to go back and figure out what it is. They are multiples of what every time? Of 3. So we have y equals 3 to the x. Now here's where it doesn't fit our pattern. Normally, we would say, okay, what do I have to add on to the end? And you go across from 0. But if I put 0 in for x, what is anything raised to the 0 power? No. 1, exactly. Thank you, Andrew. Anything raised to the 0 power is 1. So it doesn't fit our pattern when we talk about exponential. Okay, so when you get an exponential one today, remember it doesn't fit our pattern and you're not going to be adding anything onto the end. All right? Everybody okay with that? Yeah. Okay. So now let's get to those examples that Marley's been asking for. It doesn't matter. Example number 1. This is problems 1 through 3. Graph. 2. Determine if linear or nonlinear. All right, here's my x and my y. Let's say I have 0, 2, 1, 5, 2, 8, 3, 11. So you go to your graph, and we're going to plot these and see if they end up in a line. 0, 2, 1, 5, 2, 8, and 3, 11. Are they in a line? Okay, so then we just say it's linear. If your dots don't make a line, you say nonlinear. That's your first 3 problems. Yes. Except, well, actually, number 1, it doesn't give you a graph, but 2 and 3, it does. Go ahead. Nope. Just the first 3. Okay. Example number 2. Example number 2. Do you need me to move that back down in? Okay. All right. So this is going to be 4 through 7. Write a function rule for the given points. All right. So the points are going to be listed like this. Let's say I have, let's go 0, 2, 1, 3, 2, 6, 3, 11. Let's go 4, 18. All right, so they're listed in points, but for us to do our loops, we have to put them into a what? Table. So we're going to put them in a table. Here's our x and our y. My first point is 0, 2. Then I have 1, 3, 2, 6, 3, 11, and 4, 18. All right, now we have to write a function rule. So in order to do that, we have to do our what? Our loops, exactly. So 3 minus 2 is 1. 6 minus 3 is 3. 11 minus 6 is 5. 18 minus 11 is 7. Do they match? Go again. 3 minus 1 is 2. 5 minus 3? 7 minus 5. So after 2 sets of loops, they all match. What does that mean? Yes, y equals x squared. Now, plus 2, how do you know that? Very good. What is the only one, Keegan, that doesn't work with that? Very good. Awesome. All right, so do we need another example of those two problems? Okay. This also, I said it was 4 through 7, but it also includes number 9. So I'm going to put a little comma and a 9 there. I guess you'll find out in a minute. Oh, that just means a function, and we're going to hit that in this chapter. You're going to know exactly by the end of this chapter what that means. Okay? All right, example number 3. This is going to cover number 8. Yep. The rule. A equals pi r squared represents the area, very good, of a circle. States the independent variable and dependent variable, and explain your reasoning. Are you noticing I'm getting you to try and explain things a little more often to me? All right, so first of all, we've got to decide. We have two variables up there. We have A and we have R. Which one out of A and R is our independent variable? Okay? Very good. The radius can change. But can't the area change? There we go. Okay. So our independent variable is the R or the radius. That means our dependent variable is the area or A. Now, explain our reasoning. I think Joel just had a great reasoning. The area depends on the length of the radius. Wasn't it? All right, any questions? All right, let's get your worksheet. There's 9. Thank you very much.